Okay, we're going to take a look at the backside. Again, I'm trying to keep these so that it's not too long a video, but I want to make sure we talk about these. So this is kind of a good example of something you'd see. It says a raffle was held by this high school to draw for a $1,000 plasma television. 2,000 tickets are sold at $1 each. What's the expected value of one ticket? So if you think about it, you have sold 2,000 tickets. One ticket is going to win because there's only one TV. So the probability of winning this is going to be one out of those 2,000 tickets. One ticket out of 2,000 is going to win. That means my probability of losing the complement rule is 1,999 out of 2,000. So now, if you think about the outcomes, the two outcomes here are either you win or you lose. Now, I don't want you to put it in terms of thinking about it. It costs you $1 to play. So you hand over $1. If you're in this camp and you don't win, you lost $1. So 1,999 out of 2,000 people lose $1. One person wins. But if you think about it, the TV is $1,000, but you paid $1 to play. So you, in actuality, your return is plus 999. So you basically bought a TV for $1 in essence. And that happens 1 out of 2,000 times. So the expected value of the ticket is that -1 times 1999 out of 2,000 plus, in this case, positive 999 times 1 out of 2,000. And when you do that in your calculator and you add that up, what you're going to find out is on average, you're going to lose 50 cents. Basically, what this is saying is if I am the person running the event, I like this because what this means is I'm going to make money. And if you think about it, they are going to make money. They bought a $1,000 TV. They sold $2,000 worth of tickets. So again, $1,000 TV, they sold $2,000 worth of tickets. They made $1,000. What they did is they made 50 cents off of every dollar invested is basically what it is. Because even though that one person won, the vast majority of the people lost. So in this case, from the perspective of you, I mean, playing the game, you lost, but you know, you were gambling $1 versus a $1,000 TV. So I mean, this is one of those ones, but on average, this would say it's not a game to play because you're most likely to lose. So, okay, I'm going to jump around a little bit. I like this one because this one actually makes you have to think about it. So what ends up happening is 30 free tickets at the beginning of the class period. Suppose at the end of the period, 3 tickets are drawn out without replacement. Okay, so without replacement means I'm going to take the ticket out. I'm not going to put it back in. The first person wins $100. The second person wins $50. The third person wins $30. Okay, so this is a little bit different because it's without replacement. So if you think about it, what are the expected winnings? So when you walked in, you didn't pay any money. So this is no zero, there's nothing we're subtracting out of it. We're just looking at the winnings. So the outcomes here are you either are going to make $100, you are going to make $50, or you are going to make $30, or the vast majority of the people, you're going to make nothing. You win nothing. So those are my outcomes. Those are my X's. The probability. The probability of that is there were 30 tickets. I picked the first ticket, 1 out of 30. Okay, I am not going to put that ticket back into the bucket. So what I'm saying is when I go to pick the next person, when I'm going to pick the next person, what we're going to find out is that that next person only has 29 tickets worth of picking. 1 is a winner. The next person is going to have that 1 winner out of 28 tickets, and then the rest. Now, here's the thing. Since the denominator changes, this probability, you got to go to the calculator to figure out, and there isn't really a fraction for this, or the fraction is going to have such an enormous denominator that we're not going to kind of want to write it down. Basically, what it is it's about 89.8965. What I did is I did 1 minus 1/30th minus 1/29th minus 1/28th. That's what I did. 1 minus 1/30th minus 1/29th minus 1/28th. So now the expected value of this, what is the expected value? It's the $100 times 1/30th plus the $50 times 1/29th plus the $30 times 1/28th plus technically 0. You don't win, times 0.8965, 8965. And what you're going to find out is the expected value on this is $6.13. So that ticket that the teacher handed you as you walked in was worth about $6.13 on average. So that's your expected winnings. So if your neighbor offers to buy your ticket before the drawing, what you'd want to do is you'd want to charge $6.13. If you charged anything less, you would be losing money on average. If you charged anything on more, you'd be overcharging for it. They would be better off just not doing that because they would lose money. So I wanted to talk about that one. Thought that was a pretty good one as well. And then the last one, or the last ones I want to talk about number 12, because number 12 is a really good one as well. Number 12 says, a department store wants to sell 8 purses that cost the store $40 each and 32 purses that cost the store $10 each. If the purses are wrapped in 40 identical boxes and each customer picks a box randomly, each customer's expected value, if you pay $15 a box. So again, if you think about it, you either have the expensive purses, so there are 8 of those. There are 8 that are pricey. There are 32 that are not as pricey. So there are 40 total. There are 40 total purses in the box. It took me a second to remember. 40 total purses in the box. So what this says is, from the customer's perspective, your outcome is you paid $15. If you got a $40 purse, you made $25 because you bought a $40 purse for less than it cost. If, on the other hand, you got one of these $10 purses, you paid $15 for a $10 purse, you in essence lost $5. And the way that that works out, the probabilities of those are 8 times out of 40, because there are 8 expensive purses, 32 times out of 40, they're cheaper purses. And we're going to go ahead and say that the expected value for the customer is going to be 25 times 8/40ths plus -5 times 32/40ths. So the expected value here, when from the customer's perspective, is going to be $1 plus $1. So in other words, you're going to, on average, make a deal on this one here, even though the majority of the time, even though if you think about that, the majority, 4/5 of the time, you're going to be overspending for a purse. On average, this is a good deal for you. You should take the risk. Then it says, from the department's point of view, what's happening? Well, if you think about it from the department's point of view, it's the exact opposite. For them, the department is going to lose $25 every time you get an expensive purse. So 8 out of 40 times they're going to lose $25, and they're going to make that $5 32 out of 40 times, the exact opposite. And so their expected value is the exact opposite here. They're going to lose $1. In essence, if a department store came up with this deal, whoever came up with this deal should probably be fired, because they basically made a deal where they're losing money on the long run. And if you do the math to think about it, if you bought 8 purses for the store at $40 each, you spent $320 on the expensive purses. If you bought 32 purses at $10 each, you spent $320 on the cheap purses. You spent $640 on purses. Now, what's going to happen is on this one, if all of a sudden we do 40 boxes at $15 a pop, $40 at $15 a pop, what's going to happen here is 0, 4. They're only going to collect $600 for $640 worth of stuff they spent. So they spent $640 to buy the purses. They collected $600 from customers. They lost $1 on every box they sold. So this would be a bad deal for the store. Now, if it was like to draw people in, sure. you know, you're giving up $40 maybe to bring people in the store to buy stuff. But if you're trying to make money on this, you're definitely not making money. The customers are making money on this. So hopefully that helped. I will have another video that'll kind of go over what we talked about in class today. Please use the reflections to ask me any questions.